Let's get started. So it's my pleasure to welcome Debra Wunch to give our SOCAAR seminar this month. So Debra did her PhD at U of T in physics with Jim Roman, and so after she finished, she went to Pasadena and worked at Caltech with Paul Wimber as a postdoc, and then she has come back and started a faculty position just recently back in physics. So she's one of the very few people that I know that actually left Canada, went to California, and then came back to Canada. I don't know anyone else.
Any good people?
And none of the good people. Anyway, Deborah's research is on greenhouse gas measurement, trace gas measurements, and she's part of two very big projects measuring greenhouse gases from the ground up and also from space. And she's going to be very humble, but those two projects would not have succeeded without her involvement. And she's made really, really good measurements. They're very precise and also really good spatial resolution that help us understand the carbon cycle. So with that, let's welcome Debra.
I disagree about whether they would work without me, but all right. Well, it's a great pleasure to be here. Thanks for inviting me. And I'm going to talk to you about global and urban measurements of greenhouse gases today, and actually about the two projects that were just mentioned. So I just wanted to frame my research thinking, and what I'm really interested in is the carbon cycle, which is the exchange of carbon between the atmosphere, the surface, and the ocean. And it's influenced by changes in what we call the sources and the sinks of carbon. This is often in the form of carbon dioxide, but it can also be in other carbon-containing atmospheric molecules like methane. So you can release fossil fuels, you can burn fossil fuels and have anthropogenic releases of carbon-containing molecules. There are changes in land use, clear-cutting forests, and so on. There's respiration and photosynthesis of plants, the breathing and expiring of plants. And there's also uptake and release by oceans. And this all sort of fits into one big picture, and it's pretty important to us humans because without this carbon cycle, we wouldn't be able to inhabit this planet. Okay, so we know a lot of what we know about the carbon cycle, the modern carbon cycle, from a single atmospheric record of CO2. And this is known as the Mauna Loa record. And I'm sure most of you have seen this before. And this is sort of the canonical record of carbon dioxide in the atmosphere. It continues to be taken from a site on top of Mauna Loa in Hawaii. It's, I'm sure, beautiful. And if you could get a chance to go visit there, I'm sure that would be great. And we've learned a lot from this record. So you can see several things from it. You can see the slow and continuous increase, and that's due to us burning fossil fuels on the planet. You can see that there is a strong seasonal cycle on top of that, and that's basically because of the boreal forest. It breathes in predominantly in the summer. In the growing season, it has much more sunlight than it does nighttime in the summer. So it grows and grows and grows and grows and takes CO2 out of the atmosphere in the summertime. And then in the wintertime, it respires more because there's not so much sunlight up there. And so that station that takes those measurements at Mauna Loa is part of a global network, and it measures in situ. So it measures on the surface, there's an instrument, air flows through the instrument, it measures exactly how much CO2 is in that volume. And there's this big global network of these kinds of measurements, and these are what you would consider to be the gold standard. They have extremely high precision and accuracy. They take a lot of time and effort to calibrate their measurements, make sure they're as precise as possible, to make sure that the measurements taken up here and the measurements taken down there are exactly comparable. And it's all calibrated to something called the World Meteorological Scale. And people spend their entire careers defining what this scale is, making sure it stays constant throughout time and that it's well understood. And so you have here the current network, or the network in this plot is from 2013. It's got decent global coverage, but there are clearly gaps in it. And you have things like this track. This is a ship track. You have aircraft that have these kinds of calibrated instrumentation on board, creating vertical profiles. You have flasks, or you have these samplers that sit on tall towers, and you have ones that are closer down to the surface. But if you want to get global coverage, you really need to do this from space. kind of impossible. You can't have an infinite number of surface measurements, but you can have one measurement for space. You can have one satellite. But in order to get global coverage, you need to actually measure through the entire atmosphere. You can't just sample the volume of air that comes into your instrument. So this kind of a measurement is called remote sensing. And in the case of this particular satellite cartoon, it's looking down at the surface at sunlight that has been reflected off of the surface and goes into the instrument. And so the sunlight is absorbed by CO2 going down, it's absorbed by CO2 coming back up, and then the satellite instrument measures the amount of CO2 in the path. So when you have this, you need some way to tie these kinds of measurements to that gold standard I just spoke about, the ones that are so super well calibrated and highly precise and accurate. And so the way that you do that is that you place an instrument on the ground that is higher precision, higher accuracy than the satellite instrument, and you have it look up directly at the sun, and you can calibrate that using these gold standard measurements. So there are some advantages and disadvantages of this kind of a measurement, the one that goes all the way through the atmosphere, and they're called total column measurements. So this is a picture of a caricature of what the CO2 profile might look like as a function of the time of day. So this is the altitude on the y-axis and the carbon dioxide mole fraction on the x-axis. And so you can see that throughout the day, in the morning, you have very high CO2 because plants are respiring down close to the surface. And as the day progresses, the planetary boundary layer gets higher and higher, and then plants start photosynthesizing and take CO2 out of the atmosphere. This would be a sort of summer day. And so you get this kind of a picture. But when you're measuring in situ, let's say down near the surface, you get huge swings of maybe 80, 90 parts per million down near the surface. But if you measure throughout the entire total column, which is essentially a mass-weighted average throughout the entire column, you get changes that are much, much smaller. So we have instrumentation that's much less precise and accurate than the surface in situ measurements, but our signals are much smaller. So we've given ourselves quite a challenge here. And so you can see that as well in this kind of a picture. So if you look at, this is CO2 on the y-axis and just time of year on the x-axis. This is a few seasonal cycles in Park Falls, Wisconsin. The black measurements are from the in situ measurements, and you can see a really big seasonal cycle, lots of variability from day to day, and a much more muted seasonal cycle from the total column measurements. But one of the advantages of the total column measurement is that we are completely insensitive, or almost completely insensitive, to the height of the planetary boundary layer because we integrate up. We're just counting the number of molecules of CO2 from the surface to the sun, period. It doesn't matter if it's at the bottom or the top of the atmosphere. So that has some nice advantages as well. So this is where the Total Carbon Column Observing Network comes in, TCON. And this is a network of ground-based remote sensing measurements that can help tie the surface in situ network to the satellite measurements. And this is a current look at where our TCON containers live in the world. And they're designed to measure globally consistent, precise and accurate total column amounts of carbon dioxide, methane, CO, and a couple of other waste gases as well. So our objectives are to constrain the global fluxes of carbon and improve our understanding of the carbon cycle, and to provide the primary validation data sets for satellites that are measuring CO2 and methane and other trace gases. And this is a short list of the ones that are currently either on board GOSAT and OCO2, previous ones like Skiamaki, and future ones like GOSAT2, OCO3 in a sense. And we also provide this transfer standard between the satellite measurements and the ground-based network. So how do we do this tie between the satellite measurements and those gold standard measurements? Well, we ask our friends in the aircraft community very nicely if they would go and fly over our TCON stations, and in general they're pretty happy to do so, especially if they're nearby little municipal airports. So this is an example of some of the measurements that we got from HIPPO 1, which is the Higher Pole-to-Pole observations campaign, where they flew from the North Pole to the South Pole and back, and they did this in this sort of nauseating pattern where they would fly at altitude and then dip down and come back up and then keep flying, dip down, and I just don't know how they did it. I think there was a lot of gravel on that plane. And they did that like for weeks. And one of the wonderful things that they did for us is near this station in Oklahoma, they did a mist approach at a nearby municipal airport. And they got these beautiful profiles of carbon dioxide, methane, N2O, and carbon monoxide, very, very close to the measurements that we were making. And their measurements, of course, are tied to this WMO standard through actual calibration. And so this is what you get when you take the sum of all of these aircraft campaigns, and we've had the opportunity to have many people kindly fly over our stations, and you compare that to our total column measurements from the ground. And so on the x-axis is the aircraft CO2 integrated up throughout the whole column, and then the y-axis is our measurements from these ground-based remote sensing instruments. And you see a very tight one-to-one correlation with a slight offset. And that offset is basically due to the fact that we rely on spectroscopic line lists, which aren't particularly accurate. And so what we do is we take this slope, we divide all of our measurements by the slope, and we're now on the same scale as the WMO. And so we can be placed on the same scale as this gold standard, and we can also be compared directly to measurements from satellites that measure the same quantity that we do all over the world. Okay. And so I just wanted to show you that we see similar things for the other molecules. This is methane, N2O, CO, and water as well. And this is what our time series looked like as of a couple of months ago. Our measurements started in 2004 at Park Falls, Wisconsin, and at Lauder, New Zealand. So this is on the y-axis is latitude, and time is on the x-axis, and the colors just indicate the concentrations of these various molecules, CO2, CO, and methane. And you can see as time goes on, we add more and more and more and more stations, which is wonderful. We are still missing, most of the equatorial region, and that is mostly a geopolitical problem more than anything. So we've done several things to sort of try to advance our understanding of the carbon cycle. We've been able to constrain model seasonal cycles. This was shown in 2007 that models generally have too weak a seasonal cycle of CO2. That was shown by Zhonghua Yang et al. We've been looking a lot at quantifying emissions of methane in megacities like in Los Angeles, and I'll talk about that in a lot more detail in a minute. We've been looking at the health of the terrestrial biosphere and how changes in surface temperatures impacts the boreal forest's ability to take carbon dioxide out of the atmosphere, which is really important for future climate impacts. And we've also used these data to look at hotspots of methane from space, such as the one in the Four Corners region where there are a couple of very large power plants. But I wanted to focus on two separate projects. One is the urban emissions from the Los Angeles basin, which is a project that's just sort of wrapping up right now, or a piece of it is wrapping up right now. So have you guys been to LA? Many of you? Yeah? LA. We're in LA, in Southern California. Okay, so LA is a big soupy mix of pollution and emissions and all sorts of fun stuff in the air. And it is inhabited by about 17 million people, about 40% of the state of California. And this is what the topography looks like. So this is the Southern California Air Basin, so-called SOCAAR. And this is a topography map. So these are mountains on the northeast and southish, and the Pacific Ocean is to the west. And so you get this really well-constrained air mass. And so with the sea breeze, you get a sloshing in of this air mass during the day and sloshing out back over the ocean at night. There is a lot of methane emitted into the LA basin, about 400 gigagrams per year. And that is significantly more than what the state-of-the-art inventories would have, we believe, which is about 0.26 teragrams per year, 260 gigagrams per year. It's a strong greenhouse gas, and so we were initially really interested in this problem because you would think that with methane, the sources are pretty limited. If you could figure out how much there was, you get a really big bang for your buck if you could turn off the sources and stop emitting this kind of a greenhouse gas into the atmosphere. And this is a lovely picture of, fog. So we have TCON stations in the in the SOCAAD. There were 2 stationed at the Jet Propulsion Lab, which is about 10 kilometers away from Caltech, just a little bit north. They were operational over 2 years in 2007, 2008, and 2011 and 2013, and they were equipped with standard measurement detectors that measured methane, CO2, carbon monoxide, and N2O. And since 2012, we installed a TCON station at the California Institute of Technology in this gorgeous building that was equipped with a standard detector, and additionally, we put a second detector in that can measure ethane, acetylene, NO2, and HCN. So some pretty interesting molecules that can help us do some urban air measurement. Oh, I wanted to point out that this is what the JPL instruments look like with the obligatory palm tree in the background. And this is what our spectral range looks like. I don't know if you guys use spectrometers very much, but there are 3 separate detectors on which we measure a variety of different trace gases. So this is what the time series looks like from Caltech since 2012. You can see the seasonal variability. This is CO in the top here. And you can see some very fine structure in here as well. And in fact, this isn't noise. This is actual diurnal signal. So if you look at this plot, so this is from 5 days in March of 2007, I think. You can see that on all of these days, except for one, you get, in CO2, you get an increase till about 2 p.m. in the afternoon, and then a drop-off again, an increase, a drop-off, increase, drop-off. This day is funny, and I'll explain that in a minute, and an increase and drop-off. And you see very similar patterns in CO and methane as well. And it turns out that if you do back trajectories on these days, you see that the air arriving at our station has seen a lot of urban air, basin air, on the days where you get these increases until 2 and then decreases after that. And on the days where the wind comes straight over the mountains, this is the Mojave Desert up here, it's clean, there's no emissions, you basically get no diurnal variability at all. And so we were pretty convinced by this that this change that we're seeing over the course of the day is actually related to excess methane being emitted into, or CO2, or CO that is coming into the air mass that we're sensing, like the air mass of the LA basin. And so from that, we're able to look at tracer-tracer anomalies. And you can take the CO anomaly versus CO2 anomaly, and you get some pretty nice correlations between the 2 of them. So this does not imply that there's a common source. It's not all, the methane and the CO and the CO2 is not coming out of the same smokestack. But it's all being mixed into this big sloshing air mass that goes back and forth every day with the sea breeze. But if we know these correlations, we can actually compute the emissions of, say, methane if we know the emissions of one of the other gases. And in the SOCAAD, we know carbon monoxide emissions pretty well. We have biannual smog testing. They have sensors all over the place. And so they have a pretty good basin-wide estimate for these CO emissions. And so if we know the CO emissions, we can compute emissions of methane, and we can compute emissions of CO2. So we got this value. We got a value of about 400 gigagrams of methane per year from that type of analysis. And so we set out to say to ourselves, well, where is it all coming from? And from our measurements, 1 molecule of methane from a cow looks like 1 molecule of methane from the natural gas industry. And so we needed some other metric for trying to figure out where this methane was coming from. And so we started to think okay, so what are the sources of methane in the Los Angeles atmosphere? Well, they can come from cows. They can come from landfills. They can come from wastewater treatment plants. They can come from natural seeps like the La Brea tar pits. They can come from the oil and gas industry that's actually exploring for oil and gas and extracting it. And it can come from pipeline quality natural gas. So what can separate out these types of sources? And one potential answer is ethane. Ethane emissions come from natural gas in the petroleum industry. The cow does not emit ethane, and landfills don't emit ethane, and wastewater treatment basically has negligible ethane. So if we can measure ethane and methane simultaneously, we might be able to partition the methane and figure out what some of its sources are. And so that's why we set up the Caltech container to have both the standard molecules, carbon dioxide, methane, CO, as well as ethane and a variety of other molecules. And so we can now look at a record of methane emissions since 2007 from this combined set of measurements. And you can see that it hasn't really changed much since 2007. It's all sort of around, with some scatter, about 400 gigagrams per year. And just to sort of lead you in the general direction, the delivered natural gas to the SOCAAB also didn't change very much over this time period, sort of giving away the punchline before we get there. And we can show that our results agree well, so these green squares here are from completely independent measurements, mostly in situ measurements from around the basin as well, and they agree pretty well with our results. So now we can look at methane, ethane, and acetylene emissions since 2012, because that's all we have from Caltech. And there's been basically no decrease in methane since 2012 from our most recent measurements. There has been a small but significant increase in ethane emissions since 2012, and basically no acetylene changes in emissions. And acetylene is a tracer of vehicle exhaust, and so we were thinking, well, maybe, and ethane also can come from vehicle exhaust. That was one of the sources of ethane that does not also produce methane. So we were trying to rule out or include traffic as a potential source of ethane. And according to our measurements, there's basically been no change in the ethane that comes out of the tailpipes of the vehicles in Boston. So this is a complicated plot, but I'm going to walk you through it. So in 2007, there was a little bit of a leak at a storage facility in Playa del Rey. So the way that the natural gas industry works, at least in LA, and I think that it works that way here too, is that they have these huge storage facilities. It's basically depleted oil wells that they fill up with natural gas. And this is great sort of for the consumer because they can then dump a whole bunch in, and when there's a lot of demand, just draw it out faster, and when there isn't so much demand, they can just leave it and fill up the storage tank. So it gives them a little bit of breathing room in terms of how much natural gas we need to be piping into the basin at all times. But this one at Playa del Rey, and it's a pretty small one, it had a leak. And so, as with everything in Los Angeles, they were sued. And as part of the legal settlement, they needed to publish the ratios of alkanes in their natural gas to a public web page, which they do in some back corner of a web page that I found. And they're required to publish the last 3 years of those data. And so every month I download the latest file. And so now I have a record since about 2009 through 2016 of the ethane to methane ratios in the natural gas that is withdrawn from the Playa del Rey facility. And what's interesting, so this is these brown diamond shapes. And it was sitting at about 2.5%. It dipped down to just below 2% in 2012, and then it started to increase, linearly increase, with no sort of end in sight between mid-2012 and 2016. So this is pretty fortuitous because we can see a significant increase in the ethane to methane that we see in the natural gas that they report as being withdrawn. And we've also, since about 2013, have been taking samples of natural gas from our lab, running it through a GC, and analyzing the ethane to methane ratios in those. And those are these gray diamonds here. And you can see that those are increasing with a lot more scatter. And this is a very precise measurement. There are error bars on there. They're just smaller than the point size themselves. So it's also increasing, and if you fit a slope, it's the same slope within the uncertainties as the slope of this brown line. And then you look at our blue square measurements here, and those are the measurements of the atmosphere. And we can see the same increasing trend with about 2/3 the slope, 60% of the slope. This is pretty suggestive that what we're seeing in the atmosphere, especially this increase in ethane, can be almost fully explained by the increasing ethane in the natural gas delivery system itself. This also implies that just below 2% of the gas delivered to the basin is being emitted in the form of fugitive emissions. 2% is quite a bit bigger than the less than 1% the gas companies claim to be leaking. And this is a pretty big problem if it's post-consumer meter. If it's pre-consumer meter, then they're losing a lot of money. If it's post-consumer meter, they're not losing any money. So I suspect that they would have noticed that accounting problem And that is the most likely explanation for this, is that post-consumer meter, there are just tiny leaks in everybody's home of this, and that the methane is just sort of leaking at a slow rate out into the atmosphere, and we're able to see it. And another way of looking at this is to look at the Caltech ethane to methane ratios on the y-axis and the Playa del Rey ratios on the x-axis, and you get the same slope of about 60%. And so this sort of changes the way the budget of methane looks in the SOCAAB. This is the original budget from the California Air Resources Board, where natural gas is about 10% of the total budget, and this is what it ought to look like now. That's from the natural gas industry. And I wanted to just touch on, I don't know how many of you followed the Aliso Canyon gas leak that occurred. So for 112, 113 days. So here's the Aliso Canyon facility. This is JPL Caltech. This is the Playa del Rey storage facility that I spoke about earlier. For 112 days, natural gas just poured into the atmosphere. One of these wells had a massive leak. This is one of the largest leaks in U.S. history of natural gas. This is an infrared picture. You can go online to YouTube and see actual video of this. It's pretty astonishing. But these black clouds, this is an infrared camera, and methane, of course, absorbs in the infrared, so it looks black in these pictures. It's just an enormous amount of methane just spewing uncontrolled into the atmosphere. And there's an estimated almost 100 gigagrams, almost a quarter of the annual methane was released into the LA atmosphere in 3 months. And we see it in our data. So this is the time series, and then this is the period during which the leak was ongoing. And you can see we had never seen, this is methane and ethane, we'd never seen values of ethane and methane as high as we did in those few months. And you can see sort of the evolution of a day, and when it's the highest peak, we can see that the back or the forward trajectories go right over our station from the leak site. I'm going to skip over this. And they stopped the leak with great difficulty. They poured brine and cement in to kill the well. And in the end, they actually needed to dig a second well in at depth to be able to drain it. And this was a huge, clearly there were lots of suing. There was lots of suing going on because of the states. And they had to relocate a lot of people in the area, mostly because of the mercaptans. It gave people headaches and made them feel ill. It's not a long-lasting problem. But they did eventually seal the well, and you can also see a video on YouTube of the moment that it stops. It just stops. It's pretty amazing. But we learned quite a bit from this in that, while these are important, these kinds of leaks, and they obviously ought to be stopped and prevented, it was 25% of 1 year. But these leaks are ongoing. They go, like these tiny leaks that are 2% of the natural gas infrastructure, they go on and on 24/7. So it's really dwarfing these kind of big events, even though these are much more dramatic. And even further, if we go and look at the impact of the methane has, even taking into account its 25 times global warming potential of CO2, it's less than 10% of the CO2 emissions in the basin in total. And so if we really want to do something about the global warming potential of the basin itself, we need to start tackling CO2 emissions, which is a much trickier problem because it comes from everything. So that was the first part of this talk, and now I wanted to touch on the Orbiting Carbon Observatory 2, which is a pretty exciting satellite instrument that is currently on orbit as we speak. And I just wanted to give you a little bit of a sense of why I'm so excited about these measurements. So there are 3 instruments that have measured carbon dioxide total columns from space. The first is Skiamaki, and it ran from 2002, and it finally failed in 2012. It had a really good 10-year run. It covered about this much of the planet in a month. The Greenhouse Gases Observing Satellite was launched in 2009. It has a coverage that looked like this over the course of a month in 2014. And then the Orbiting Carbon Observatory, launched in 2014, has this coverage in the course of a week. And so we're really breaking open the ability to see fine-scale structure in the carbon dioxide of the planet. The footprint size is small, though never small enough. We always want to get smaller and smaller. Clouds is the biggest problem in terms of getting a higher yield of measurements. And when there are clouds, which there typically are in the tropics, it's hard, you can't see through them, so those measurements get thrown away. But we're really starting to enter a data-rich era in terms of the global carbon cycle, which is very exciting. So OCO2 has 3 viewing modes. It has the native viewing mode, which I showed you earlier. So sunlight reflects off the surface, absorbed by carbon dioxide along the way, reflects back, and goes into the satellite instrument and absorbed by carbon dioxide on this path as well. And that's the nadir measurement. That's good over land, generally only, but it has very good latitude coverage. It gets pretty much up to the poles. Glint mode, if you've ever been on an airplane and looked out the window and seen a really bright spot on the surface, that's the glint spot. And so that's what glint mode is. The satellite turns and looks off to the side at the brightest spot on the surface, and that gives you really good land and ocean measurements, but it has a poor latitude coverage, and so you don't get all the way up to the poles, which are pretty important for the carbon cycle. And so and then third mode is something called target mode, which is a really neat idea that they came up with for this project. And in this mode, the spacecraft actually turns and stares at a point on the ground. And this is a map of the locations of the current, although it changes every so often, current situation for the ground sites. And most of them are TCON stations, that network that I described earlier that can tie into the gold standard measurements. And this is what a target mode measurement would look like. So the satellite rotates away from its nominal position, stares at a particular point on the ground, sort of nodding back and forth, measures as it goes overhead, and then switches back and points its solar panels back to the sun. I guess I'll let you watch that one more time. Sorry?
It's fun.
Yeah, it's fun. And so it can do that a couple times a day. If it does it too many times, it loses power, and so we're careful about how many times we tell it to go stare at something. And we make lots of decisions about where to target, and we use the weather forecast for that particular location, whether the ground station instrument is actually running, whether we've gotten measurements there lately, and we try to make these decisions in a timely manner and inform all of the ground station PIs that we're going to target them. And this is a bunch of pictures of the various target points on the ground that we have successfully obtained. Well, we weren't so successful over Bremen, but we've obtained some measurements, some target mode measurements. And these images are from the MODIS satellite, which is also in the A-Train, the same sort of constellation of satellites as OCO2. So we can really see what the status of the viewing was for those particular measurements. And so, as we did with TCON versus the aircraft, we can now do the same thing with the satellite versus TCON. So this is the calibrated, so-called calibrated TCON XCO2 measurements on the x-axis and the satellite measurements on the y-axis. And you can see a pretty nice, not perfect, correlation between these two. The R-squared is about 0.8 or so. There's some scatter, but in general, the satellite is doing well and it's actually seeing CO2 from planet Earth, which is pretty great. And while it's doing well, there's still definitely some problems with it. And so right here, I have the ground target sites going from the northernmost site in Eureka, Nunavut, down to Lauder, New Zealand. And this is the difference between the OCO2 measurements and the TCON measurements. And you can see that there are definitely differences from site to site. And for example, Edwards Air Force Base, which is just basically north of JPL in the Mojave Desert, measures quite low on average. And a place like Wollongong, Australia, measures quite high. And we're still working very hard on trying to understand why that is. But just to give you a flavor of what this looks like, so the black points here, this is the time series of time and XCO2. The black points are the TCON measurements from the ground. The colorful points are from the various different viewing angles, viewing modes from the satellite. You can see that they track quite nicely for this particular site. which is in the middle of the country in the US. And for Wollongong, you can see that there are definitely some problems. The difference between CO2 from OCO2 and T5 diverges quite a bit in the summer for the Southern Hemisphere winter of 2015, and we're still trying to work out the cause of that. And we also know that things like surface properties get in the way. So on the the left-hand side here, this is a target over Lauder, New Zealand. This is what the image is in the background. The target, the T-CON station is under the star, and this green, the green colors here show the topography, so the altitude of the surface. And so the brown colors are highest and the green colors are lowest. And this is the CO2 over the same region. There is no reason to believe CO2 changes over this small extent over the course of a few seconds. And so any variability we see in this, we know is spurious. And so we start to look at potential causes for these biases and see if we can correct them either in the algorithm and the physics, update the physics of our algorithm, or do some sort of post hoc correction of the data. And so this is something that we're all working on very hard at the moment. But I just wanted to give you a bit of a flavor for what the measurement sequence looks like at the moment while I sum up. And so I think, I hope I've convinced you that, that these atmospheric measurements are pretty important to understand the carbon cycle, and that we're in an era now where we can start to look at, urban megacity emissions and also global carbon cycle questions. And T-CON is a pretty important part of this, as it is higher precision and accuracy than the satellites, but can measure the same quantity, and so it's important to tying those measurements from the satellites to the surface in situ network. And that OCO2 is doing reasonably well, and we clearly have some warts left to resolve, but the team remains pretty focused on trying to resolve problems. And I'll let you watch as the CO2 builds up in the Northern Hemisphere wintertime in this series. And I think that's all I have, so if you have any questions, I can take them now. Questions?
Do you suspect, back to the methane, can you suspect that there's like post-consumer in the household, you think indoor measurements would help constrain them?
Maybe. My guess, though, is that it's tiny. Certainly, okay, so everything I know is anecdotal. Everybody I know who lived in LA, like everybody they know, seems to have remembered some massive leak in their house at one point that they didn't find for weeks. Right? Like they accidentally left the pilot light, or the pilot light turned out in their oven or their furnace or whatever, and it was just going, and you couldn't smell it because it went up the flue, and so it was fine. Like I know that my furnace had to be serviced, and it was something like 5 ppm there coming out of my furnace, but I didn't smell anything because it was just being vented. And my, Paul Wenberg's house has, several hundred fittings in his basement, each of which could probably be leaking a tiny amount, and you wouldn't notice unless you really went down there and started sniffing around. So I think it's pretty hard, maybe, but I think it would be pretty hard. Yeah.
Related to that question, so previously it can be increased, almost annually, last 3 years, right? So is there any
methane increase?
Yeah.
Yeah.
So is there any surface area, surface measurement? Some VOC measurement around the LA principal site, or some sort of increase of methane or some propane?
I haven't looked at the propane. There have been other measurements that, so everything we've looked at cannot explain the ethane increases except for the increases of ethane in the actual liquid natural gas. We looked at traffic, we looked at, like oil and gas extraction, That has remained basically constant. The liquids that they've extracted in the basin has basically gone to zero in the last few years for some reason. Propane, I looked at the propane extraction but not measurement, so I'm not sure that's really worth commenting on. Yeah, we can't think of anything else that could have caused the ethane increases.
Go back to the graph that showed the increase from the 2016. I was trying to do a sort of mental calculation. You said it was 25% of the annual amount was released in those about 100 days or so, 115 days. You had a time series graph before that showed the really sharp spike. There we go.
Yeah.
So I was trying to ballpark it. If we had 25% more in about a third of a year, that would be almost a doubling of the concentration. But it seems like it's way more than that.
The doubling of the concentration.
So I'm trying to figure out if you ended up putting up 25% more in just a portion of the year, then that would make it up by, if the emission rate was up 75% or 0.75%, I guess.
But this is a doubling in the change from the background, not a doubling in the overall value. And that is essentially what you're seeing there.
Well, that looks like more than a doubling. It looks like it looks like quite a bit more for that period.
I don't know. You think that to that?
Maybe. Okay. So
I wouldn't read so much into this plot, but I think it's
So that's where that estimate came, the 25%?
Oh no. This 97.1 gigograms comes from a Conley et al. Paper that was published shortly after the leak. They took an aircraft and they flew around and around and around. And so they estimated about 100 gigograms of methane. And that is a quarter of the 400 that we measure annually.
I think there may be a way to get that similar estimate from those graphs there as well to see.
Yeah, I think it's possible. I wasn't quite willing to stick my neck out, but
I'll go for
it. Yeah, I think it's possible. Yeah.
Does water in the atmosphere affect CO2 conflict?
No, we divide our CO2 by oxygen measurements. And so they're both influenced in the same way by water, and so it ratios out. It's the dry air mole fraction that we get as our result.
I was going to ask the exact same.
Really? Okay. Great minds think alike.
I have a comment and a question. It was very impressive data that you presented and work. So my first general comment is your conclusion concerning the fugitive emissions, of just the many fugitive emissions being overwhelmingly important versus the very large leaks. It was the same message that comes out of oil tankers in the oceans. That's whereas these huge leaks are very publicly visible, it's in fact a constant leak from our oil and gas consumption. And the second comment, if you go back to the first part of your, the end of the first part of your presentation, in which you showed the improved coverage of the CO2 estimates. But what I was also impressed with was just the rate of increase in the carbon dioxide concentration up to 410 ppm. And I noticed you didn't comment on that.
Oh,
it was it was a
what?
Yes, that one. Yes.
Yeah.
Yes.
So that's just the color bar scale. I don't think any of them on a monthly average reach.
But just looking at the changes in colors of the predominance.
Depressing, isn't it?
Yes. Which any other comments? I mean, it's an astonishing rate.
I mean, in the surface, like Mauna Loa has now, this is the first year where it's not going to dip below 400 in the entire seasonal cycle. This is the way it's going.
And for example, do your trends coincide with Mauna Loa with that long time? Well, that's a bit much longer time.
Yeah, so if you were to plot these over top, there would be some differences, but the rate of increase is pretty much the same. It's about 2 to 3. Well, so this year is a bit different because it was an El Nino year, and that also increases CO2 to the atmosphere. And so the growth rate this year was about 3 ppm, I think, per year, but it has been about 2 ppm per year, roughly, since we started these measurements. And I know that the Mauna Loa time series goes way back to the point where it was below 2 parts per year, but it is seemingly getting bigger.
I'll come back to the anomaly calculations as well. So we discussed this a bit by email, I think.
Yeah.
So we often do these sort of anomaly calculations, but we link them to CO2 because we have this idea that we can better get a handle on CO2 based on the fuel burned. You were saying for LA at least, CO is better known.
Yeah, so yes.
I've never quite understood how the CO is kind of all over the place for us here.
Right, so there's 2 reasons. So in the original paper in 2009, we did do it to CO2 because it is so much more constant, and we figured we could do a better job of estimating CO2 emissions. But there are a couple of reasons that CO seems to be a bit better. First, CO2 is a statewide estimate. And we are only sensitive to that small Los Angeles air basin. So we scaled down the statewide estimates to the population of the basin, so 40% of them. And we said, okay, that's the number. But it's not really clear that is the right thing to do. There may be more industry elsewhere, for example, or there may be more industry that produces CO2 in the basin, and there was nothing better we could do than just scale it by population. CO, on the other hand, they actually estimate in their inventories by air basin. The California Air Resources Board publishes CO emissions by basin itself. And so that correlates much better. That is much better suited to our purposes here because we think that we are looking at basin-wide emission. And so if they get the basin-wide emission roughly right, and it seems like they do a pretty good job, they know how many cars are in LA, they know, what the emissions coming out of the tailpipes of those cars are, and that's the main source of CO in the basin, and they can really constrain it down to that level for us. That's what made it. That's what made us switch to using CO.
Yeah, I guess that was really the question: is how do they get those emission estimates? If it is from emission factors from vehicles, it suggested they know what CO is coming out of vehicles. It's actually maybe optimistic.
Do they not measure CO from vehicles? I mean, that was a line on my smog check that I had my vehicle.
Well, they do and they don't. So it really depends what you do with the catalytic converter. It's just that's what John's been doing. They're all over the place in terms of the CO emissions for different vehicles.
So, but as part of a smog check, do they not? I mean, I think they.
They do it, but the problem is the test that they do, you might come in with a hot engine, you get one result, or you come in with a cold engine, they have a heating cycle and you test it there. And I've had my cars tested over many years, and one year it's high, next year the CO is low, then you test it 6 months later and it's all over the map.
Okay.
It just, I wouldn't put much faith in it.
And even if it exceeds it, you don't actually have to get it fixed.
Yeah.
Is it speed dependent?
It is really dependent.
Yeah.
Humidity,
So,
temperature.
in California, they do a two-speed test.
Yeah, same here.
I
No, they changed it to 1 now.
They change it to 1.
Yeah. But even then, it was all over the map.
So I get your skepticism. I think I'm not sure what to say other than it's corroborated by independent measurements that don't use the CO. It's pretty similar to actually I get a little bit higher results if I use CO2, but I'm not super confident in the scaling to population.
But we don't know the CO2 either, so it's not going to
Right.
criticism.
Right, so I do depend on knowing something. I
You gotta
have to
know
assume something, and so I assume CO is correct. Yeah, that's a weakness, definitely. But it's
So with organic aerosols, they ratio it to CO as well. And the argument is that they come from the same incomplete combustion. Right? So if it's a complete combustion, it goes to CO2. If it's a complete combustion, it goes to hydrocarbons and maybe CO. Right, so that was the argument, at least for organic earth. It might be the same for
When you calculate the anomaly, how do you determine the baseline for the
Right. So I take, this is a bit complicated, but so basically what I do is I take the afternoon value at a particular solar zenith angle and I subtract the morning value at the same solar zenith angle. And I do that for all the solar zenith angles throughout the day. The reason I do that is because we have, in the TCON data, we have like an air mass dependence due to spectroscopy, and I wanted to avoid being influenced by that. But that's the way I do it.
Yeah, it's an interesting challenge.
Indeed. Yeah. Oh, I guess that was the part that I was going to get to, and I never got there because I stopped at the movie. Because I was going to talk a little bit about what I plan to do here. So the second project that I was thinking about was looking at emissions from Toronto, and I'm hopeful that I can work with many of you in this room to do this. And one thing that I want to do is, so we don't have a big basin, a soupy basin in Toronto where we have this nice diurnal flow, and so instead, the idea that I'm working with right now is to place one of these remote sensing instruments, a smaller version of it, upwind and one downwind of the city. And then you can get anomalies by simply differencing the two measurements that are taken at the same time. And so you can get the same kind of anomalies and relate them to anomalies, so CO anomalies related to CO2 or methane related to CO2 and CO, and try to do the same kind of analysis for Toronto itself. And then to do some more pinpointing of methane emissions is try to compile maps. I had a couple of talented undergraduates working with me this summer, and they took an old instrument that they got an inverter for, and they walked around with a cart throughout campus, and they took measurements of methane concentrations throughout campus, and they saw some differences from north to south, but it was never really clear exactly what was happening. They just did this the last month, but they had a great time walking around, and this is the sort of thing that I'm hoping to do in a more wide-scale version in Toronto, to try to narrow down what our emissions are and maybe where we can reduce them. Yeah.
One of the challenges is figuring out what's upwind.
Yes.
Versus downwind, because
Yes.
the windrows is actually surprisingly well distributed.
Yes, and so one of the student this summer used some back trajectories and looked at seasonal dependence of the upwind and downwind, and it looks like we may have to move the instruments throughout the year, but it looks like for most of the year you can do sort of west-southwest and east-northeast as upwind and downwind respectively, and then that'll have to shift a little bit in the spring and summer. Spring is just a mess. We may never get spring. The winds come from everywhere. But for the rest of the year, especially in the wintertime, you get some pretty strong southeast to northwest, southwest to northeast winds. So yeah, we did look at that a little bit. Definitely tricky.
Winter, southwest and northeast?
Northwest. Yeah, northwest. Yeah.
Sometimes we wish it was from the south.
Indeed. Yeah. And so, yeah. So we did look into that. And that's going to inform where we try to place these.
In the interest of time, thanks for a very illuminating talk and some exciting work that's going to be ongoing. So, thank Debra.
Thank you.